So, any questions about z-scores, calculating z-scores, finding a raw score from a z-score? Does the whole concept of a z-score kind of at least make sense? A little bit? A little bit. Okay. Okay. Not Greek, but probably not really sure what the relevance of all of this is. That was something that was asked here was, you know, in my line of work, has there ever been a time when I've needed to know the z-score of something, or I've needed to know the raw score that equated to a z-score? And the reality is no. I have never had to do that. There is somebody that has already sat and calculated all of that information for me, so if I needed to know it, I would look it up in the back of the book. What this does, though, in terms of practical application, is that it gives you the conceptual understanding for the transformation, the concept of knowing the relative standing of a score. So that when you look at different types of tests, IQ tests or other standardized tests, or in psychology or human services, if you're giving behavioral checklists and you come up with a T-score, you're going to have an idea of what that means. So that's kind of the conceptual and theoretical underpinnings for why it's important to know about z-scores, even though a z-score per se, I've never had to use one. Okay. But it's still important to know how to interpret them. So, what do you think a z-distribution is? What's a z-distribution? How far z's are from each other. A z-distribution is going to be a set of z-scores. Yeah. Okay. So the z-distribution is just that. It's a set of z-scores that are then graphed, you know, in a distribution, just like we did our frequencies. That's all it is. But to interpret them relative to now to the z-distribution, the first thing you have to do is obviously transform all of your individual scores into a z-score, if you really felt the need to do that. Those scores are going to be listed along your x-axis, your horizontal axis, and the frequency of each of those is going to be along the horizontal axis. So now you're basically doing a frequency graph of all your z-scores. So the graph that I had up there at the very beginning, we could conceivably calculate the z-score for a 5, a 6, a 7, an 8, a 9, and a 10. And now it has suddenly become a z-distribution because it's a group of z-scores. Okay? Now, in a z-distribution, just like in the curve, in the standardized curve, where the mean is 0, do you all remember that part, like when we were talking about the standard deviations, where the mean falls, that value is 0, and then you've got 1 standard deviation above and below, 2 standard deviations above and below, and so on. You do the exact same thing with the z-distribution. The mean value in a z-distribution is 0. From there, the numbers are going to go out. So our z that we got was 1.197 standard deviations above the mean. Okay? So the closer that to the mean the score is, the more frequently it occurs, which is just like in a standard deviation. The more frequently it's going to occur. Now, the further it is, the less frequently. So the larger the value of the z, the less frequently it's going to occur. A z-score distribution is not going to affect the shape of your data set. Why is that? The data set is raw scores. Why is the Z distribution not going to affect the shape? Why will the shape not change? Because it's the same. All we've done is we've changed that X, the raw score, into a Z score. It doesn't affect the shape. It's just transformed your score. It's not changed the score, per se. A 9 isn't suddenly going to become a 9.5 or a 10. It's still a 9. It's just we've transformed it from a 9 into a 1.1972 value. So it doesn't affect the overall shape. When we look at standard deviations, because remember the Z-score takes that into account just like it takes the mean into account, the standard deviation on any Z-score is 1. So Z-score distributions are going to be 0, 1, 2, 3, 4 positives, -1, -2, -3, -4. If you all look, then let's go ahead and look at this. I'm going to put it up on the full screen, and I think it will make more sense. Okay? So here, what you can see, okay, what you can see is the 0. Okay, look at the standard deviation line. That's the very first row of numbers. So the standard deviation, the mean represents 0, because we're looking at deviations from the mean. You've got 1 standard deviation on either side. Let's see, am I going to be able to get in there? I'm not going to be able to get in there. Okay. So do you all see where the 68% is then? Because you've got your 0 right here. That's your mean. 1 standard deviation above, 1 standard deviation below. That total is 68% of your scores. Okay? That's where most scores are going to fall. So when I'm doing behavioral checklist, that is considered the average range. That's where most scores fall. That's the average range. When you start going above 1 standard deviation or below 1 standard deviation, that's a little less typical. Okay? On one of the forms that I gave you all that we're not going to go over, but just to kind of help you all think about it, maybe in a little bit different perspective. 1 standard deviation below and above is average. Most of your scores occur there. If it's between 1 and 2 standard deviations, either above the mean or below the mean, that's kind of considered your at-risk range. So you're at risk for greater difficulties in those areas. Okay? If you're at that point, we kind of want to watch, we want to monitor how things are going, because you could develop even greater difficulty. You're getting away from the norm of what we would expect. Okay? If you get between 2 and 3 standard deviations above or below, how frequently do those scores occur?
Rarely.
Rarely. You're starting to get into the tails at that point. You're only capturing about 2% of people scored in that range. Okay, that's very few. 4 total if you consider above and below. Very few people. So when I'm doing the behavioral checklist, if I'm at that point, I'm saying that's a clinically significant, that is a definite difference compared to what we normally expect to see. Okay? So that's what the standard deviations then are going to tell us. Now, if you look down a couple to right here, you've got your z-scores, okay? Look very much like the standard deviation line. Your average is 0. The standard deviation is 1, 2, 3, 4, -1, -2, -3, -4. Okay, so that still indicates to us how frequently the scores occur. Does that make sense seeing it visually?
Yes.
Okay. Okay, now the ones that I use a lot in my work is the T-scores. T-scores have a mean of 50. So on average, the behavior checklist, I would expect to see a score between 40, well, technically 41, because that puts it right inside one standard deviation. 41 to 59 is considered average. Okay. If I get a T-score between a 60 and a 69, that tells me that kiddo is at risk for greater difficulties. Let's say I'm looking at depression or I'm looking at hyperactivity. If I get a T-score of 65, that is saying to me that child is at risk for greater difficulties from depression or from hyperactive behavior. If I get that kiddo who is 70 or above, that says to me this is a definite difference, and this is something I really need to look at for this particular child. Why are they so hyper? Is it ADHD? Is it sensory issues? What is it? I don't know just from the scores, but what it tells me is that's dramatically different. So here are the Z-scores and how they relate to the standard deviations. And a common one that you all will see in your work are the T-scores. Okay, now I also gave you all, I hope you all got them, some other handouts. Did you all get one that is called the distributions of standard scores?
Yeah.
Maybe.
Did you all get it there? And
Oh, we had this, which is,
yeah, those are the behavior checklists. I'm not going to go too much into that because I don't want to confuse you all.
so we have those, but that's it.
All right, you did not get the one that looks like this?
Oh.
No, ma'am.
No.
Okay, well, I will resend that to you all then. But what this shows is, and it didn't copy very well either, but what this shows is like GRE scores for graduate school, and it shows ACT scores, and it shows the IQ scores on here. So those are just some other practical uses of Z-scores in those transformations, the standard scores on there. And those may be some concepts that you all may be a little bit more familiar with when you're looking at ACT, SAT, GREs, and that. So you get a raw score, they do their transformation, and it spits out an ACT score of 550. So if the mean, the average ACT score is 500, and there's a standard deviation of 100, what would one standard deviation above and below the mean be?
Say it again.
Okay, that's your the line that's not showing up very well. All right. Back to line, your mean, which is 500. Okay. If you've got a standard deviation of 100, one standard deviation, what scores would be one standard deviation above and below the mean?
600 and 400.
Perfect. Yes. So if you get your scores back on your ACT and you've got a 440, you are in the average range. If you get an SAT or an ACT score of 700, what does that mean?
Above average.
Yep. 700 is right here. This is 1, 2, minus 1, minus 2. Okay, so now you know relative to all of the other scores where your score is. You know that you got a score of 700, you know you're way up there, and you're going to be in the tail at that point because it's going to go like that, right? So between 400 and 600, 68% of people fall between those scores. And then it goes out from there. Was it 13%, I think? There, and then essentially 2%. So you know, relative to everybody else on that test that day, where your score falls. So does that kind of help make it, give it more meaning as to why we talk about this and why it's such a powerful transformation? Because we can do the exact same thing with IQ scores. It's 100 is average. The standard deviation on an IQ score is 10, depending on the instrument that you use. But if a standard deviation is 10, then average is going to be from 90 to 110. You've got an average IQ if your number is between there. If you go up to 120, that's above average. Real original name there, but nonetheless, it's above average. If you go out to a 130, that range right there is superior. And I have tested some kids that have fallen in that area. Okay? So relative to everybody else that has taken this test, those are the norms. So when they talk about norming standardized tests, that's what they're doing. They're calculating the average score on the test. They're calculating the standard deviations. So then we know relative to everybody else in that sample where that person's score fell. And usually they standardize tests on a couple thousand people from all over the country, so that hopefully it's as representative a sample as possible. So that's why we talk about standard deviations and z-scores. So it can be applied in multiple different ways. Okay. All right, we talked about standard scores. Okay. Let's see here. Where do I want to go with this? All right, so we're almost through the z-score chapter. What time is it? Okay. Another thing to know, and I'm just going to mention it to make sure you're questions don't cover it, so I want to make sure I cover everything that your questions are going to want. 1014. Okay, so number 10 we've covered. 14 we've covered. 18A. Okay, we do need to talk about the relative frequency. Okay, so z-scores, as with most everything else, can be used to determine the relative frequency of the scores in a distribution or in a set of data. Again, the relative frequency is that proportion of the whole that a particular score represents. And what this is going to do is it's going to start taking us back a little bit to that concept of the area under that we talked about a couple chapters ago. Okay? The relative frequency for a score is going to be the same on every Z distribution, as long as it's normal. It's going to be exactly the same. Okay? Because it's standardized. That equalizes everything. So keep that in mind. Z-scores contribute to standard scores, which is the great equalizer. Okay? A z-score is always going to be located on the same, at the same place on any distribution that you have. So one z-score above and below, if you're looking at depression scores, is going to be the same place in the distribution as one z-score above and below a measure of hyperactivity. It's always going to be the same location. Okay? So, what I'm going to have you all do, and do you all have this particular one about finding the relative frequency of the z-scores?
Yep.
Okay. So see if you can figure out what the z-scores are, the z-score, the f, and the relative frequency for our data set.
The frequency.
Like that one.
Okay.
Standard deviation is 1.42.
Yep, you already actually have a lot of the information.
So
Okay.
Z, to find a z-score, you gotta have 7.0 minus. Zero, 9. Lowest score.
It's down at the bottom. So we have to figure the Z for each one of these.
How many spots do we go out for, you said?
Yes. So we do all of this except for instead of putting 9 in it, we put like 10, 8, 7, 6. Sorry.
Tracy, you're fucking with me.
It's really complicated. So numbers 4. She's 9. Got the 5 without OG. How do you round that?
So is it 0?
Okay, how far back are we
0.493?
going and all this calculating? How did we come up with? You want to know where'd you go back?
I went to
Which formula?
this one. The x equals z.
Okay, but don't need those.
You're going to the b divided by your standard deviation. That's what we got our 0.1. 1.904.
This is Z.
Got all the information.
Can we do this on the board?
Right, that's your mean. That's the standard deviation that we've already obtained. There's your z-score formula.
So are we looking for the Z score? Is that our first step in this process?
Yeah. Well, the first step that you've got to do is find the relative frequency of each of the z-scores. That's what you're doing. So yes,
Do we have to find the Z score first?
it's up to you. You've got all of the information available to find the z-score.
Oh, well.
Okay.
So,
The formula for the z-score is the raw score minus your mean divided by the standard deviation.
can you write that up there? I'm confused.
It's on the slide. On the bottom of the slide.
No, but I don't know what this means. Okay, what? It's really blurry.
Right, that got really blurry, didn't it?
Okay, so that's how we get to Z.
Where
Yeah,
is,
but what the Z-score is
Okay, and the X is your raw score, is that what you're saying?
the X is the raw score. Mm-hmm.
and it's 7.3, so Z is 73.
How do you do that first step? That's how many times it occurred now? Out of the normal numbers, which like 1. Is that one? It's like 1 divided by 10? By n?
Relative is the
Sorry.
f divided by the m. It's 1.42. You're right about the.
Should you just say how many times?
Everybody agree?
Really?
I think
So for 10, for the Z score,
This here is this area,
oh, wait a minute.
because we had to have the X over here and not 7.3. So, okay, we had to have the mean, right? Okay, 7.3. Okay, so now.
We'll get back here and
This
be clear.
is the standard deviation.
It went really,
The times that
I didn't know
1.2.
I looked at.
it or what, was it?
You know where to start.
Yeah, I don't know how to,
Okay,
oh, there it went.
let's see.
It's 38.
It went back. See, it's you.
Right.
It's already been going on the bed.
Yeah, I used to do the relative frequency, because it's just dividing in, the frequency is 5.
Classes dismissed.
So that's, that would just be easy.
I don't know, I'm lost.
I might have it right on my version.
So that would be
I think it goes crazy negative this
0.5.
time.
So,
Okay, so do you all at least have the Z-scores?
No,
Okay.
a lot more time.
What did you end up with?
and that,
Mm-hmm.
On which one?
9
No,
Oh, great.
0.492.
Your
Already.
0.493.
numbers in there.
We'll go 4 points.
I could go 4?
Yeah.
How did I miss that up?
That's your raw score.
1.972.
So your raw score minus your mean
You have to go out to that.
divided by the standard deviation.
Cut out.
So that's going to reflect 10 minus 7.3 divided by 1.42.
So they all have. Yeah, but 0.4930 is what.
0.49.
So you divide first.
I did, it was
Oh, wait a
295, so I just,
492.
I would round it up to.
so 30. So it's okay to put 0 in there, because I think. We're supposed to put a 0.
I don't know how to round that one. That's a rough one.
I'm always.
Can we ask a question?
Yeah, absolutely.
On the z-score for 8th, if we round it to 4 decimals, would that be 0.4930 or 0.49?
You got it. 0.4930.
Good job.
The 5 afterwards. Was
Yeah.
101.
I am too.
Slow. I may be slow, but I'm
I'm
slow.
gonna work on mine anyway.
But what does, so what is the? Then I gotta do 9 divided by. That will always kill. I can never remember.
Okay, what did you say the answer was for me on the z-score?
0.4930.
Okay, that's what I'm gonna do.
Did you get negative?
Yes.
Yes.
Until I was really very too. Divide that by. Somebody.
I'm just adding a decimal point to this. 8 minus 7.4. I'm subtracting 1.4.
Oh, yes, yes.
See, I don't want to do any work on that one.
Are we doing relative frequency?
Yeah. It was relative the, no. I don't know.
What'd you get for 5? But wouldn't it round up? Because you've got the 7 on the end.
No, we did 4 numbers.
Right, but you've got a 7. Bump your 9 up.
So 10 minus 7.3.
Oh, you don't round up the 9, you just round up the 7. Or you just look at the 9.
Right.
Divide first. Okay. And then my hands have that.
Divided by 9. You calculate your minus first. So 10 minus 7.3. Yeah.
Negative. Divided by.
North, take your badge.
Negative.
2.7.
Yeah. The little green thing.
Don't just like baby.
Seven minus 7.
Okay, you all ready to see what the Z-scores are?
Yes.
Are we moving through all of this? Okay.
Yes. Add one, plus that 9 was 5.5. This. Two, 1, 3.
Okay, did you all get your frequencies? That's just kind of the simple frequency.
How come on the 9 you only went out 3 spaces instead of 4?
Oh, it should have been the 4.
Okay.
Then you all got your frequencies, correct?
Mm-hmm.
Yes.
Okay, that's the tally of how many times each occurred. Okay. And then have you all completed your relative frequencies?
Yes.
Okay. People here ready to see what the relative frequencies are? Okay. Oh, okay. Okay. Now, if you wanted to find the relative frequency of the raw scores, or of like more than one raw score, okay? Let's say you wanted to know the relative frequency of a score 5 and 6. What do you think you all would do? The relative frequency of getting a 5 or 6.
0.2 or 0.1.
Right. So we're going to add those. So to see what the relative frequency of 5s and 6s were, that's absolutely what you do. 0.2 plus 0.1, 0.3, and then we want to make it a percentage. So we're going to do our transformation, and that's going to make it 30% of our scores were a 5 or a 6. Yep. You're going to add them. Okay, so now let's think back. Does that make sense to everybody before I move on? I'm pretty sure that you've got to do this piece for your homework, so I want to make sure that we cover it. What time is it though? All right. Do you all need a break, or do you want to get through this chapter? I'm hearing get it over with at this end. What about you all out there?
I think we're good with it.
Good with it, okay. Now, if the situation would arise that you would need, for some reason, to identify the area under the curve that is above or below a particular z-score, there are tables in the book that are going to allow you to do that. Now, this is going to become relevant when we talk in a couple weeks about t-scores. So I do want you all to be able to have some general idea of how to do this. So Remember, the area under the curve is kind of like the 3D, and we're looking at the frequencies, okay? Now, what I want you to do is turn to page 422 in the back, well, obviously in the back, of your book. Okay? So there may be an instance in some situations where you would need to find the area under the normal curve. If you wanted to know that area that is below the z-score or above the z-score, so that's kind of like looking at the relative frequency. So we know that 5 or 6 is 30% of our scores. Okay? So we know that's a low frequency. No, it's 0.2 plus 0.1 is 0.3, and then we make it, we record it as a percentage. 30% of our scores are either a 5 or a 6. So a small percentage of the total scores. So how you use this table, okay? If we are looking at the number 8, now our z-score for the number 8 was 0.4930. If you look in the book, you'll notice that they are only carried out 2 decimal places. Okay, do you see the z? The area between the mean and the z, and the area beyond the z that's in the tail. Do you all see those 3 columns? Mm-hmm. Okay, so what you're going to do is you're going to look down the z column, and because it's only carried out 2 decimal places, what are we going to look for?
0.49.
If we're looking at this one right here at the 8, it's only carried out 2 decimal places. So what z-score are we going to look up?
0.49.
0.49, perfect. So you're going to go to the z that is 0.49.
No, that was
Okay. And we know that area under the curve between the mean and our z-score of 8 is 0.1979, 1879. So that is 1 z, or that is the distance. Okay? So that's not even 1 z-score, so to speak. So that's where our number 8 would fall. And if we wanted to know for some reason what that area beyond our z-score is, when we're looking into the tail, what value do you find there? 0.3121. Okay? So if you look at the little diagram up above, you've got your mean and your 1z above and below. The area between the mean of 7.3 and an 8 is 0.1879. And then we've got 0.3121 out past that. So how close to the mean do you think that is? Is it close or is it far?
It's close.
Close.
Pretty darn close. Absolutely. And we know that just from it being 7.3 to an 8. We would expect a lower number. And then there's going to be a greater amount that is beyond our score. I know that concept is a little bit more confusing. It will make more sense when we make the move into inferential statistics than what it does right now. But pretty sure there's a question on your homework that's going to require that. So that's why I wanted to make sure that we cover it tonight. Okay. Now, in addition to being able to compute a z-score for individual scores, it's also important to be able to do that for a sample mean. Okay, for the mean of our sample, for a 7.3, for instance. Because, as I mentioned, the inferential statistics start computing something kind of equivalent to that score. And again, that is going to make more sense when we start talking about the sample and inferring those results to the full population. Okay. So what we would do if we're trying to compute all of that, we would take, for instance, that the IQ testing, and we would test people in Kansas, and we would test people in Texas, and we would test people in California, and we would test people in New York, and we would test people in Florida, and maybe up in Iowa. So that we would have several different samples from all over the country so that we can see on average how people do on on that IQ test, for instance. So what we would do then is we would have all of those different samples and we would get the mean from all of those samples. So on average, the people in California had this score. On average, the people in Iowa had this score. People in Florida, this score. People in Texas, this score. New York, Kansas, I don't know if I said another one. But anyway, so we would now have all of these means from all of our different samples. And what you'll start to do is you'll come up now with a distribution of all of these different means. When we get that grouping of means, we're going to plot them. Mean scores are going to go on the x-axis. The frequency is going to be on the y-axis. Okay? This is starting to make that leap from only looking at the samples to now trying to figure out if this represents the entire population. Does that concept make sense?
Yeah.
Okay. So now you've got our raw scores now just happen to be the means from all of these different samples. But it's still just a set of data. Okay. Now, knowing that there would obviously be an infinite number of means because we certainly haven't tested all potential samples either. So again, it's never going to touch the x-axis. But the goal of this is to try and determine just how far the sample mean is from the mean of the sampling distribution. What does that mean? That means now that we've got an entire we've now got a distribution made up of means. So here are going to be the frequency. Here are going to be all of our means. That's not working because I just wiped it off. So sample 1, right here, sample 2, sample 3, 4, sample 5, sample 6. So we got all of these means that were just like they were raw scores. So now what you're going to do is you're going to get the mean of this distribution. Does that make sense why we would make that leap?
Yeah.
All of these different samples, we know on average what they were. So we now plotted out all of those numbers. Now we want to know what the mean is of all of these. Because that number then is what we're going to infer to the population. So let's say this test was done on 8 to 11-year-olds, okay? So So we've got 8 to 11-year-olds in each one of these samples. And we've got our means from each of our samples. We've got Texas, Kansas, Iowa, Lake California, Florida. I don't know if there was somewhere else that put Indiana on there. So we've got the means from each one of these samples. And that's what we've plotted. Now, just like with our other distributions, we want to know what the mean is. What's the average score that was obtained? So we're going to figure out the mean of our distribution of means. Once we know that, we're going to take that and apply it to the population. Kind of makes sense?
Why do you assume that it would be such a bell curve? I mean, it's taking IQs, hopefully they all have about the same IQ. Wouldn't Texas and Kansas and Florida all have the same kind of, wouldn't it be a
yes, and they probably would be. That's what we would hope to find, but not necessarily. But we would hope that our range is much smaller. We would like to think, because the average on an IQ test, because of how they've standardized everything, is 100, okay? We would like to think that of all of these samples, that the mean score obtained on each one was right around 100. So our range for this then, because of what you're saying, which is absolutely accurate, we would like to think that it maybe ranges from, let's say in Texas, their average score on the test was a 98. And let's say, and this was not meant for anything, let's say the average score is 103, okay? So those are very close to one another, okay? But this could be depression scores, it could be anxiety scores, it could be anything, okay? And so if it was one of those other scores, there may be a greater range in it. But yes, for IQ, we would like to think that it's right around 100. So in this case, our range is only 5. Because it's going to be 103 minus 98. But then what we want to do to infer then to the greater population of all 8 to 11-year-olds throughout the country, we're going to figure out, we would figure out what this mean is. And it may be 100, it may be slightly off of 100. But we're inferring to the whole population.
Take the largest one and subtract the smallest.
Does that help? Okay. Okay. And I just chose IQ. It could have been, like I said, anxiety or depression scores. And then you maybe would have differences in those. You know, it's kind of like if you go from one side of the country to the other. That's why they do all of these means from all over the country to try to get the average and kind of get rid of some of those differences. Like if we were doing anxiety or depression scores and I used Florida and Washington State, you would like to think there would be a big difference. You would like to think that Florida depression scores would be really low because it's sunny there most of the time. And Washington State actually has the highest suicide rate in the country. So we would expect their depression scores to be much higher. So we've got these means from all over, and then what this does is it says, okay, but now let's look at the average of all of these. And to be able then to say, okay, on average, this is the depression score of 8 to 11-year-olds.
And if the feds had money to give to a place
Right.
to treat those kids, they would give the money to the place that had the highest
Right. Right. So then you can start using this information for things like getting funding for programs and that sort of thing. Yeah. So the ultimate goal for this then is to get a bunch of samples of data, a bunch of distributions, look at the average score in each one of those, plot all of those averages, which now makes up its own distribution for a set of scores. And now we want to take the mean, the average of those. Yeah. So then what that does then is it gives us information about where California stands on their mean relative to everybody else. So in California, according to this, if we're using IQ, they're a little bit above, but they're still probably average. Versus Texas over here, which falls at the lower end. So relative to all of the other samples that were taken, their relative standing is they're lower. Okay, and why this is important is because we're going to start here in a couple weeks and talk about T-scores, which are the inferential statistics, and you're going to be comparing different sample means. So this is that segue into that. Central limit theorem. All right, how about this? We are clearly not going to get into chapter 9 tonight, so I apologize for you all reading through that. Would you all feel comfortable go ahead and finishing out chapter 6 and then reviewing what's due next week and letting you all get out of here and doing a revision? Okay, because it's already 9:15 here.
Oh.
Okay. Now,
An hour later.
so what questions do you all have about this? With that starting to infer back to the population. Because the bigger concept to understand is just that a Z-score shows the relative standing to all other scores. Okay. And it takes into account the average score, the mean, and it takes into account the average deviation from the mean to give a relative standing. Okay, the central limit theorem is just kind of one of those conceptual ideas. And what it does is it defines the mean, the standard deviation, and the shape of our sampling distribution. The sampling distribution is this distribution of means because we've sampled from Texas, sampled from Kansas, sampled. So it's a sampling distribution. Okay? And so what this allows us to do is describe the sampling distribution without having to get scores from every single member of the population. Because that would be impossible. There's no way that you're going to be able to test every 8, 9, 10, and 11-year-old across the country. Okay. Now, again, as you might suspect, the sampling distribution generally has a normal curve shape. It's a normal distribution. The mean of the population equals the mean of the underlying raw score of the population. So that little mu sign for the sample, our symbol for mean is the X with the line over it. For a population, it's that. It's the mu. So when you see that, that stands for the population mean. And the population mean is going to equal the mean of the raw score distribution. Because again, we're inferring it, we're predicting it. So that kind of goes back to predicting. Without any other information, predict the mean. So whatever this mean is, that's what we're going to predict is going to occur in the population. So similarly, because the mean is the same, the standard deviation is also expected to be the same. So the standard deviation of the raw score the raw scores there should equal that of the population.
What is this little zero
Which little zero?
with the hat on it?
Oh, for that one, that's going to be the standard error of the mean. Okay. So that brings us to the last concept for tonight, which is the standard error of the mean. What do you all think that refers to?
How far off is acceptable?
How far off is acceptable? Okay.
Standard deviation.
It brings into the standard deviation, it's standard. So we're looking at kind of the standard. And what is error? We referenced it a few chapters ago. What is the error? Error equals what?
Deviation.
The deviation, very good. Yes. So it's the standard deviation from the mean. So it represents the standard deviation of the sampling distribution that we've got up on the board. It's the average amount that the sample means, which is what we've got along the x-axis, deviates from the mean of the sample distribution. So when we were talking about just a regular sample of scores, we calculated the standard deviation, which is the average amount that the scores deviate or differ from the mean. The standard error of the mean is just going to be the average amount that these means deviate from the mean of this distribution, of all of these samples.
I don't get this one on it. It has that symbol, and to get it, you have to know that symbol.
Well, it's just the way they do that population. I can't do the little mean thing. So yeah, they are different.
Oh, so is that, those aren't the same symbol?
They're not the same symbols.
Oh, okay.
No, they're not the same symbols. So the standard error of the mean, again, is going to be the average amount that the scores deviate from the mean of the sampling distribution. Now, to calculate that, the formula for the true standard error of the mean, you've got the symbol, okay? It's going to be the standard deviation divided by the square root of n. So mu equals the mean. The other with the x equals the standard deviation. And then n, of course, is going to be the total number of scores. So in our case, we've got 6 means, so your n would be 6.
So it's divided by?
Yeah.
Divided by.
Mm-hmm.
Okay, can you start over on that? I'm confused.
Okay. So,
What symbols?
okay.
O and X.
Yeah, the standard error of the mean is going to be that O symbol.
Okay. With the X, that's what that means?
Yeah, I wasn't able to get that in there. Well, it doesn't work very well. Okay. So the standard error of the mean, and this is the symbol for the standard error of the mean. Okay?
Okay.
And then your formula for that
What does that mean up there on top?
okay, so that up there on the top is going to be, oh, I thought you were answering it. Yeah, yeah. It's the standard deviation divided by the square root of n.
I thought standard deviation was ST.
That's for the sample. We're now talking population. We've made the leap from sample to population.
So that means standard deviation in the population?
Yes.
3 hours. Oh,
Yeah. We're starting to make that leap.
Yeah, just one was a population, the other one.
So how do we get these numbers?
Yep. So the formula, then your standard deviation of the population is expected to be the same as that for the sample.
So what numbers are we using? Are we actually doing a problem right now?
No,
Okay.
no, I'm just letting you know how you would calculate that. Yeah. So it's just a matter of whether we're talking sample or whether we're talking population.
And the only difference is that one little line over the X, right?
Right, right. Yeah, the standard error of the mean is going to be the standard deviation of the population, which is assumed to be equivalent to that of our sampling distribution. And your n is going to be the same as the other end. It's going to be the total number of scores.
So I thought that U thing was the population.
It's the population. That's referencing that. Yes,
Population, not the mean.
it's the population mean.
Okay.
Yeah.
Yeah.
So that is going to be the standard deviation.
Okay.
Okay.
Divided by
Divided by the square root of n.
Okay.
Mhm.
Yeah. So what is that exactly?
So does that clear up the language and how to read that formula? Okay. Okay. And then the next thing that you would do is you can calculate the z-score for the sample mean. I'm not going to have you all do that. You've already done that on the sample. But as you can see, it starts using population symbols because we're now making that leap to the population.
What were we doing before?
The sample. So when we had, so here's kind of what we got.
Right, before we was doing math, now we're doing behavioral science.
So before, we had our sample, and I don't even remember now what it was, but we had, what, we had 5, 6, 6, 7, 7, 7, 8, 8, 9, 10 maybe, something like that. So that was our sample. And we figured out our mean, which was 7.3. We figured out our standard deviation, which was 1.42. Okay, so we figured that out for our sample. Now imagine if we did that several different times. Okay, so let's call this sample 1. All right, and the mean is 7.3. So let's put that about right there. And that's not showing up. It'll show up here in a minute, I think, when it dries. And let's say we took another sample, and that sample had a mean of 6. Sample 2 was a 6. We did it again. For some reason, that one had a mean of, and then we had another sample, and their average was 3. Okay? So now we have all of these samples, and we have the means from each of those samples. This was just one sample, one distribution. Okay? So now we created a sampling distribution. It's the means from each one of the samples, the groups of people that we tested. Okay? And then we would technically have here our frequencies.
So the sample would be like if I just tested one classroom, and the population would be like, okay, I'll sample class 1, class 2.
Yep. Yeah. Okay. So we've got each one of these samples, and we've now plotted all of the means. We're going to come up with the frequencies. We're going to assume that it's probably that. Okay. So then in looking through this then, the central limit theorem, what that says is that the sampling distribution of means is always going to be approximately normal. Okay, so there's our approximately normal curve. It is going to have a mean, okay, the little mu sign, in the population. What we're going to infer to the population is whatever mean we have here is going to equal that. So our sample mean, we're going to infer, because it's a normal distribution, and it's going to equal that in the population. Okay? Likewise, the standard deviation, well, the standard, you all can't even see that. Okay, then the standard deviation of our distribution of means is going to equal the standard deviation in the population. Again, because it's a normal distribution. So that's what is presumed in the central limit theorem. That what we find from the sampling distribution is going to equal that in the population. But then, of course, just like in our sample, our mean was 7.3. Not every score is 7.3, right? There's going to be some deviations from that. Okay? A 6, the deviation is 1.3. The 8 is 0.07. Okay? This right there is 0 because that's the mean. Well, 7.3. Right. Close enough. Okay? So then it starts to deviate. So what the standard error of the mean now, because we're talking a standard curve, we would expect then that not every score is going to equal the mean of what this whole distribution is. So that's where we're starting to talk about now the standard error of the mean. It's the standard amount that these scores deviate from this mean. Does that make sense? Okay. A little bit? Okay. And I know it's late. at this point. And it does start to get a little bit more convoluted at this point for everybody. So what I want to do now is take a look at the syllabus, because there is no way in the next 4 weeks that we are going to get to absolutely everything. So, what will we do for next week? Next week, what is going to be due is Chapter 6 questions. Okay, so the Chapter 6 questions that you'll fill out for next week are numbers 10, 14, 18A. Only do the first one on 18. Number 22 and number 24.
Can you repeat that?
Yep. Questions 10, 14, 18A, 22, and 24 for Chapter 6. Those are what's going to be due next week. So next week then, in terms of the reading, we'll get to Chapter 9 and Chapter 10. So reread Chapter 9 and read Chapter 10 for next week. Also due next week is the introduction to your independent projects. Now I'm going to send out to you all the data set for this. What I want you to do is I want you to do 2 samples. Okay, so you're going to divide it up, and I will have them divided for you into 2 different samples. Okay, I know that in the project, it talks about using the ANOVA. We are not going to get that far.
I'll mark out number 8.
Yeah, we are not going to get to the ANOVA in the amount of detail that you all would need in order to use that for that paper. Okay. So I'm going to change it up, and what you're going to do is you're going to use what is called the t-test. Okay, but because you're supposed to say, how do you know that in number 8 under the introduction, it says, how do you know that ANOVA is an appropriate analysis for your dependent variable? You're not going to know that because we've not talked about ANOVA, and we're not even going to get to ANOVAs, I don't think. We will probably talk briefly about it. I'll let you know what it is, why it's used, but I'm not going to have you all calculate all of that. Instead, I'm going to have you all calculate the t-test. And what I will do is I will give you all kind of a synopsis of what a t-test is when I send you the scores that you all will use. Okay? So then that way you all can make the application just from that. And that portion of it will be scored very late. We've not even talked about it. Okay, so that's kind of you all taking a stab at it.
Is it an APA or one of those just answer questions?
Good question.
Online thing.
Good question. On this one, because it's the introduction, at this point, I'm going to say just answer the questions. Don't worry about APA yet. Okay. APA, though, will come when you all do the completion part of the project.
So, okay, what is due next week on this?
So next week, you're doing the introduction. So if you look at page 7 on the syllabus,
Uh-huh.
right below the statistics and the media assignment, it says the independent project introduction.
But anywhere it says ANOVA, disregard that and put T-system.
Yep, disregard that.
T-test.
I know, it makes me go work.
So I'm going to send you all the scores, your data sets that you will be using. I will have them already divided into 2 groups, 2 samples that you all will be using. And then I'm going to give you the blurb about a t-test. And then you all can use that to take a stab at why it's the appropriate test to use.
And the subject is the matter that we emailed you 2 weeks ago.
Correct.
Okay.
Correct.
So that's the topic.
That's the topic. Yep.
What?
Okay.
Yep. So any questions about that?
What topic?
And I'll do a review of it when I send out the scores to you all.
I'm assuming it'll make more sense when you send us your stuff.
Exactly. Yeah. Yeah. And I think it will. But just know, that you all are not going to have to go out and do your own research. I'm sending you your data. I'm sending you information on the t-test so that in that 8th one you can answer, how do you know that the t-test is an appropriate analysis for your dependent variable? Okay?
Because our instructor told us so.
Well, pretty much. And I have had people it's because that's what she said. And it will be. So you'll have that due, you'll have chapter 6 questions, and then next week we really need to work on getting through both chapters 9 and 10 on probability and hypothesis testing.
From what I read on chapter 9, if you know how to do Z-scores, chapter 9 is good. I don't know.
Really?
Yep. You know how to do Z-scores. The first paragraph says, now that you know how to do Z-scores, this chapter will be easy.
Well, and very honestly, chapter 9 on probability, you all are very familiar with probability. It has to do with odds. It has to do with chances. I mean, if you're betting on basketball games, then you're going to be able to figure out probability and chances and odds.
If you figure out Z-scores, you got chapter 9.
Yeah. Yeah. So any other questions from out there in Kansas?
Yeah, can you send me the email of the updated syllabus? Because I don't think I got that.
Yes, I sure will.
You know that.
Oh, that she has a YouTube channel. She made a YouTube channel.
Maybe you might try to put up the-
Were you all able to access that? Speaking of that,
Yes.
you all were. Okay, I just wanted to make sure. All right then, you all have a good week, a good night, and I'll see you next week.
Thank you.
Channel.
Or about the midnight, because I was doing something.